Good morning. This is from Mitchell and Son 3D Printing Services. This is a early morning little notice, which is, and I shouldn't be too long. Over the last couple of months, the last year, apparent, when we have quoted for 3D printing metal parts for the classic car market, we've had a number of concerns because people are saying, well, how strong is the metal? Is it trustworthy? Is the strength there? So it's one of those things we've tried to always reassure because and there are many, and the way metal 3D printing is advancing and the technology is advancing is quite phenomenal. They have various different ways of ensuring that. Again, there are different processes, there are different materials, there are different providers, there are different manufacturers who make the 3D printing metal or the powder, because the way the 3D printing metal is turned into a powder, it's atomized. So it's turned into fine powder. But then there are other 3D printing manufacturers that will are taking that powder and putting it into filament, which is on a roll, and then that can be then 3D printed and then sintered. So what sintered is that they put into a kiln to get rid of all or vaporize all the plastic and then fill the voids. But that's not my concern today. So a number of customers have come to us, and recently we've had a few which have said, well, how strong is the metal? Can we trust the metal? So if you look at the metal data sheets, because there are many available on the internet where you can view to see what metal is being used, and a lot of metal manufacturers or metal 3D printers will actually provide you with those data sheets. And if you want any data sheets from us on steel or aluminium, then let us know. Those are the two most common metals that we would quote for 3D printing. And there's a few things that if you don't know, and I'm sorry if you do know, so I don't want to speak to you as if you're ignorant. So I do apologize for that. But there's a few things on the data sheets that need understanding. So the HRC, or the hardness of the material, is quite important. And if you think of how hard is a piece of steel, the HRC, a good HRC, and one which we can all have a look at, is a pocket knife. Normally has an HRC rating of around 57 to 59. How do they test the hardness of material? They take a cone shape little dome with a diamond on the end, and they will press that onto the piece of metal or onto the object that they are testing for hardness, and they will apply a constant pressure to it to cause an indentation. When that machine stops, when it can't press in anymore, the hardness of the material is determined by the depth of the indentation. So when it comes to 3D printing metal, again on the data sheets, you've got to understand what they are. So what is tensile strength? Tensile strength is the ability to resist the breaking under a constant stress. So they'll take a piece of metal, they'll put it in a machine, a special machine that is designed to either pull it apart or bend it to see what the breaking point is, and that then is calculated, the tensile strength, which is measured in MPa. So it's the pressure on that. So what is the yield stress? So they test the yield stress, and that is the pressure, the constant. So it's not a varied pressure; it's a constant pressure that is applied to metal. And so it says the definition is the yield stress is the minimum stress at which a solid will undergo a deformation or turn into a plastic flow or becomes a liquid, or start becoming solidified without significant increase in the load or external force. In other words, they will apply a constant pressure onto the metal to see when that metal starts to give way, and become what that's called like a metal flow. In other words, the metal starts to move freely, but it's a constant pressure. So they don't increase the pressure. So they will put a constant pressure and see when does that eventually give way. Now, steel, a definition or a comparison that we can compare this to. Now, we all know titanium is really a hard, good quality, enduring metal. Pure titanium, at grade 1, the tensile stress is 240. The yield is 170. The elongation is 24%. So in other words, it'll stretch 24% longer, so that the percentage of elongation is 24% of the overall length of that item. The elastic modulus is 102.7. That's at grade 1 for titanium. At grade 4, the tensile stress is 550. The yield is 485. The elongation is 15%, and the elastic modulus is 104. Well, I'm telling you that for a reason. So you can keep that in your mind as I tell you 3D printed material. So the 3D printed main, or the big metals that are often requested with 3D printing is titanium, aluminium, and steel. So the tensile strength of 3D printed titanium is 900. You compare that with a pure grade 4 titanium at 500, that's quite big. The yield of 3D printed titanium is 830 MPa. If you compare that to grade 4 titanium, pure titanium, that's 485. So it's almost double. The E modulus of 3D printed titanium is 110 GPa, where if you compare that to grade 4 pure titanium, that's, what did I say? E modulus 104. So the grade 4 titanium, pure titanium, is 104. 3D printed is 110. The elongation at break for 3D printed titanium is 10%. We're comparing that to the elongation. So, I mean, okay, the elongation on 3D printed titanium is slightly less. It's 10% rather than 15% on pure grade 4 titanium. Now, if we look at aluminium, and again, I'm going to compare that to titanium for the purpose of this exercise of grade 4 pure titanium, because it helps us to understand in our minds the strengths and the differences. So titanium, the tensile stress is 250, and if you compare that to grade 4 titanium, which is 550, so it's half of grade 4 pure titanium, but the tensile strength of grade 1 pure titanium is 240. So 3D printed aluminium, the tensile strength is 10 points higher than grade 1 pure titanium, which is amazing. The yield on aluminium is 180. The yield on grade 4 titanium is 485, but on grade 1 titanium, pure titanium, the yield is 170. So again, on aluminium, it is higher by 10 points, which is, again, amazing. It is brilliant. Okay, the elongation on aluminium is 1%. Means it's gonna break quite quickly, a lot quicker than it would on titanium. Titanium grade 4 is 15%, grade 1 is 24%. The E modulus on aluminium, 3D printed aluminium, is 70 GPa, where on grade 4 and grade 1, it's over 100. So again, obviously being aluminium, it is going to be able to break a lot quicker. Is weaker than titanium, but does compare in a lot of in the strength, the tensile strength and the yield, so the break strength of in comparison with titanium. Now, if we look at March steel, which is a 3D printed steel, if we compare that again, I'm going to compare that again to grade 1 pure titanium. So if we look at the grade 4 pure titanium, so we look at the tensile strength of 3D printed steel is 510 MPa. If you look at that of grade 4 pure titanium, that is 550. Very good, very good. If you look at the yield of 3D printed steel, it's 300 MPa. If you look at that of grade 4 titanium, pure titanium, that is 485 MPa. Again, very, very close to what titanium is. And remember, this is steel, which is not, it's not titanium, it's steel. The E modulus of 3D printed steel is 180 GPa, okay, where grade 4 titanium, pure titanium, is 104. So it's again higher than that's higher than titanium, which is brilliant. The elongation is 45%, opposed to 15% on titanium, meaning that you're going to get when the elongation is 45%, it's going to take longer to break. So you've got a lot more strength, you've got a lot more stability in that. Now, I wanted to share this with you because obviously it's to try and put a little bit of clarity and a little bit of assurance in the 3D printed metal. 3D printing has come a long way since the 1980s. It's moved away completely from being a purely prototype porous material, because I think in the beginning we had a lot of issues where they were trying to bring the material back. It's learning material again, learning material science again in some ways, because if you think of traditional material, that's stuff we've learned over hundreds of years. 3D printing has brought us back to we've got to all learn again. We've got to all take it back and experiment and test again. And a lot of there's a lot of money that's been poured into that at universities. Bournemouth University I know they are doing a lot of studying. I know Oxford University is doing a lot of experimentation. I know Southampton University is doing a lot of experimentation on 3D printed metals and materials. So there's a lot that's going into it. There's a lot of science and a lot of learning that's going into it. Porsche Classic is confident of the process. They're using it and they're expanding it in their classic car restoration side, because they have a Porsche Classic division. Jaguar is using it. BMW has been using 3D printing for almost 30 years. So it is a technology where the big names are using it and they are confident of it. And it's just now moving on to see that we can grow confidence in that. We can grow assured of the strength and the durability of the parts that are being produced in 3D print. I only wanted to touch on those two metals because that is the metals that we mostly quote on. And we've had a lot of people coming back and say, well, give us a bit of confidence. How do we know that it is strong enough? Anyway, That is Dwight Mitchell sending out this morning. So thank you very much if you've listened. If you have any questions, you can always email me at dwight@mitchelson.co.uk. So that's mitchellson.co.uk. Or you can give me a call on 07876 131 539. Thank you very much and have a really good day.